In this video, I want to talk about inverses. And we're going to start by talking about inverse relations, but we really want to focus on inverse functions. First of all, when they exist, and if they do exist, how to find them and what it means. So let's talk about an inverse relation first. So let's say we have a relation R, and that relation is from A to B. Then the inverse relation is the relation from B to A, where the elements are just swapped around. That's called the inverse relation of R. It goes in the opposite direction. Let's do an example here, just some easy ones, just to make sure we get the idea of what an inverse relation is. Here's R1. Let me draw it out in terms of sets here. So here's A, here's B. We have 1, 3, 5, A, B, C. So R, I guess R1, which I'll do in red here, says each of 1, 3, and 5 are related to A. The inverse relation, which we usually define by a little -1 subscript, I'll do this in blue, just a little -1 like this, it literally just reverses the arrows. It's a relation that goes in the opposite direction. So it starts from B and goes to A, and it just reverses all of the arrows. So that's what an inverse relation is, and we can write that down. So R1 inverse is the set, well, we have A is related to 1 via R1 inverse, A is related to 3, and A is related to 5. So we have A1, A3, and A5. And you can see what we're doing here. All we're doing is we're swapping where the first element and the second element are, because we're reversing the relation. Let's look at the next one, R2. R2, same idea. So we have 1, 3, and 5, A, B, and C. So 1 is related to C. This is R2, by the way. 3 is related to B. 5 is related to A. All right. Well, the inverse, again, we're just going to reverse the arrows. In the inverse, A is related to 5, B is related to 3, and C is related to 1. So R2 inverse is C1, B3, and A5. Remember, for the inverse, we start in the codomain and we go to the domain. The domain and codomain swap places. Now, I do want to point out something. Note that both R1 and R2 are functions. Each element in the domain of this function, the red guy here, is related to exactly one thing in B. 1 is related to A, 3 is related to A, 5 is related to A. Down here, 1 is related to C, 3 is related to B, 5 is related to A. But the inverse relation need not be a function. Let's look at this. Here we have A. Remember, this is R1 inverse, so we're starting at B and going to A. So if we input A, well, there are 3 things that A is related to. A is related to 1, 3, and 5. And similarly, well, B and C are related to nothing. Nothing here is related to exactly one element. However, down here, R2 inverse, this does happen to be a function. A is related to 5, B is related to 3, C is related to 1. So in some cases, the inverses of functions are functions, and in some cases they're not. So maybe pause the video and see if you can think about what properties of functions will allow us to take inverses and why. And then we'll talk about it briefly on this slide, and then on the next slide we'll go into more detail about it. Okay, now that you're back, well, this function here, R2, happens to be both one-to-one and onto. Each element is related to a unique element in the codomain, and so that means it's one-to-one, and every element in the codomain is related to something. And if we think about that, the fact that it's one-to-one means that we'll never run into a situation like up here. R1 is not one-to-one. This element A is mapped to by 3 different elements in the domain. So if we take the inverse of that, well, now A is related to 3 things. A maps to 3 things. It's not, you don't have a unique output for the input A in the inverse. So it's not a function. So if a function is one-to-one like R2 is, it avoids the situation where you have more than one thing related in the inverse. And if it's onto, well, that means that every element in the codomain is related to at least one element in the domain. So what that means is you avoid situations like here. R1 is not onto. This element C is mapped to by nothing. So in the inverse, there's nothing that maps C to anything. So that means that if a function is onto, it avoids the situation of having something mapped to 0 things. So one-to-one avoids more than 1 in the inverse, and onto avoids 0 in the inverse. And if a function is one-to-one and onto, then in the inverse, you'll have a unique output for every input, and you indeed have a function. So that's kind of the idea there, how the properties of one-to-one and onto relate to inverse functions. And let's talk about that a little more concretely in the next slide. So before we get into any details, I need to introduce a special type of function. This function is a relation from A to A. Indeed, it's a function. And all it does is nothing. You input A, it outputs A for any element in your set. It's called the identity function on A. The notation that we use is I of A, or you might see another one that you might see is ID of A. That means the same thing. So either I of A or ID of A means the identity function. And just to make sure we understand what's happening, let's do an example of one. So let's say A looked like this. Let's say you had the elements A, B, C. And here's the second copy of A, our codomain A, B, C, same set. All the identity does is it maps everything to itself. It does literally nothing. This is the identity on A. So now let's prove this theorem here. So let's have 2 non-empty sets A and B, and a function from A to B. Then the inverse, F inverse, the inverse relation is also a function if and only if F is bijective. And then we have moreover, if F is a function, if F inverse is a function, then it is also bijective. So let's do the first part first. This is an if and only if proof. So that means we're going to have 2 directions to go. So if F inverse is a function, then F is bijective. And if F inverse isn't a function, then F is not bijective. And if we think about it, it might be easier to kind of, if we call this P and Q, I think the way I want to do this is I want to prove Q implies P. So we'll go the backwards direction first. So assume f is bijective and show that f inverse is a function. And then we don't know too much about f inverse. It's kind of hard to write down in some sense. But we know what it means for f not to be bijective. So maybe instead of doing p implies q directly, let's do the contrapositive. So the negation of q implies the negation of p. So this is going to be our plan. Okay, so let's prove this. And it's basically going to just formalize what we talked about on the previous slide. So let f be a bijective function. Well, since it's bijective, this means that it's one-to-one and onto. So since f is one-to-one, every element A in A is related to a unique element in B, and let's call it F of A. Okay, so we know that, and we know that since F is onto, each element of B is mapped to by some element of A. So this means, thus, the relation f, remember all functions are relations, which is, say, a f of A, where A is in A and f of A is in B, has the inverse relation f inverse, which is just swapping what the A and f of A's are. So we have f of A and A, such that f of A is an element of B and A is an element of A. So we're literally just swapping the elements in the domain and codomain. So here note the following. Note that all B in B, or let's say for all B in B, B equals f of A for some unique A in A. And just to be clear, we know it's for all B because f is onto, and we know that this is unique because f is 1 to 1. So that tells me two things. So the first thing it tells me is that f inverse is a function, and f inverse is bijective. It's one-to-one and onto. each element in the domain of F inverse in B is related to exactly one element in A. And since F was a function, everything in A maps to something in B. So F inverse is indeed bijective. Okay, so just in the interest of space, I'm going to erase this. So if you haven't yet, pause the video, copy this down. You can always rewind, of course, if you need to see it again. But I'm going to erase this, and I'm going to do the other half of our proof. Okay, so now we're going to assume F is not bijective. And we're going to show that F inverse is not a function. So if it's not bijective, it means that it's either not one-to-one, or not onto, or both. So if F is not one-to-one, well, what does that mean? That means there are elements A1 and A2 in A such that A1 and A2 are actually different elements, but F of A1 indeed equals F of A2. And thus, well, what does that tell me? That tells me that in the inverse here, the inverse function F inverse, F of A1, F of A2 are the same element. Let's in fact call that, I'm going to call that B star for now. That's in B. It tells me that B star is related to two different things, A1 and A2. So it tells me that B star is related to A in the inverse, or sorry, A1, and B star is related to A2 in the inverse. So both of these things are elements of F inverse. Let's just draw a little diagram just to make sure we understand what's going on here. Here's A1, here's A2, and this isn't one-to-one, so these guys both get mapped to this element B star. So in the inverse, well, B star would be related to both A1 and A2. And everything in the domain of the inverse is not related to exactly one thing in the codomain of the inverse, so it's not a function. So it tells me, so F inverse is not a function. Now, it could be that F isn't onto. Okay. If F is not onto, well, what does that mean? It means then there is an element B in B such that F of A doesn't equal B for all elements in A. So what does that mean? So here's our B down here. Nothing maps to it. So in the inverse, there's nothing related to B. So there is no A and A such that BA is in the inverse relation F inverse, because B would be related to nothing. There's no arrows going back the other way. So that tells me again that f inverse is not a function. And we're done here. We proved both directions. And that's pretty cool. It tells you something very important about inverses. It tells you they can only occur when f is bijective. In fact, it tells you that they always occur when f is bijective as well. So that's really cool. Now, we talked about this notation here, this identity notation. The reason we did is because we want to look at the idea of composing a function with its inverse. And what happens, basically, is nothing. It just ends up being the identity function on either A or B, depending on where you start. So, let's prove that now. Let's draw a little diagram just to make sure we understand what's going on. So, again, here's A, here's B. And the idea is, we take an element here, A, we have an element here, B, and F maps A to B. There's F. And the inverse maps B right back to A. So if you start at A, you apply F to get to B, and then apply the inverse, F inverse, you get straight back to A. So that does nothing. Or you could start at B, apply the inverse, and then apply the function, you get back to B. So that also does nothing. The first, where you apply F and then F inverse, that's like the identity on the function A. And the one where you start at B, apply F inverse, and then apply F, that acts like the identity on B. So that's what we're going to show. So, we know, first of all, that by theorem 36.1 above, since F is bijective, we know that F inverse exists. And we know it's also bijective and is bijective. We like that. Okay. So now let's consider, well, let's do the first one. Let's do F. Well, let's do this one. Let's do F inverse of F of an element A, which is, of course, F inverse of F of A. Now suppose that F of A equals B, then of course F inverse of B equals A by the definition of inverses. So, what does that mean? F inverse of F of A, well, that equals F inverse of B, which equals, of course, A. So, F inverse of F of A equals A, and thus since we didn't specify anything about the element A we picked from our set A, this works for all elements. So that means that F inverse of F is the same function as the identity on A. It does nothing. And similarly, F of F inverse of B, well, that's F of F inverse of B. Well, we know F inverse of B is A, so this is F of A. and we know f of a is b. So, since f of f inverse of b equals b, well, this means that f of f inverse is the same as the identity on b. It does nothing. You start with an element of b, and you get the exact same element back. And this diagram is basically showing everything that's going on with this result. Now that we talked about inverses in general, let's look at some specific concrete examples. Let's look at this question. So we have a function f of z, and note that there is no domain written here. There's an implied domain, and in fact, we're going to have to be careful. We're going to have to figure out an implied codomain as well, because it will be the domain of the inverse function. So if this is a bijection, we need to figure out what are possible inputs that we can put in for the inverse as well. So the first thing we want to do is show this is indeed a bijection, so that it's one-to-one and onto. So pause the video now, try this yourself, see if you can figure out how to show that this is both one-to-one and onto. Okay, now that we're back, so let's do this. Let's do one-to-one first. So we're going to let z1 and z2 be such that f of z1 equals f of z2, and we want to show that z1 equals z2. That's how you show something is one-to-one. So let's go ahead. We know what f of z1 is. That's z1 minus 1 over 2z1 plus 1 equals z2 minus 1 over 2z2 plus 1. Now, let's cross multiply so we can get rid of that denominator. And we're thinking that we're going to set our domains here so that we're never going to have to worry about this being 0. So we'll talk about that in a little bit. But for now, let's cross multiply. Here we go. And I'm just going to do this fairly quickly. So z minus 1 times z1 minus 1 times 2z2 minus 1 is 2z1z2 plus z1 minus 2z2 minus 1. So that is this multiplication here. Let's do the other multiplication. So this equals, well, again, I'll do this quickly. 2z1, z2 plus z2 minus 2z1 minus 1. And let's clean up as much as we can. We have a 2z1, z2 on both sides, and we have a plus 1 on both sides. So let's subtract 2z1, z2, and add 1 to both sides. And that's the obvious thing. We'll clean it up a little more in a bit. So this simplifies to z1 plus 2z2, or sorry, minus 2z2, my mistake, equals z2 minus 2z1. And we need to show that z1 equals z2. So let's go ahead, let's get all the z1s on one side, all the z2s on the other. So I'm going to add 2z1 to both sides, and I'm going to add 2z2 to both sides as well. So we get that this is 3z1 minus 2z plus, or sorry, minus 2z2 plus 2z2 is 0. That's fine, that's why we added 2z2 to both sides. z2 plus 2z2 is 3z2, and minus 2z1 plus 2z1 is 0. Of course it is. So we have 3z1 equals 3z2, divide both sides by 3, and we've shown that z1 does indeed equal z2. So that means that f is 1 to 1. All right. Now we need to show that it's onto. And again, I will say when we talk about it being onto, we're going to have to be a little bit careful. There will be a value that it's not going to work for, but remember, we need to work out the implied domain and codomain as well. And the nice thing about the onto work is that it gives you the inverse as well. The onto proof will give you the formula for F inverse as well, which is really cool. All right. So, here we go. So, we're going to take some number b and we're going to find what z this works for. So, z minus 1 over 2z plus 1. And now we're just going to solve for z in terms of b. We're thinking of b as an element of our codomain, and we want to figure out what element of our domain do we put in here to get b out. So let's go ahead. We'll solve for z. Again, we need a little bit of arithmetic here. I'm going to multiply both sides by 2z plus 1. I really should say algebra. It's not arithmetic, although we, of course, are using arithmetic to do our algebra. So we're multiplying by 2z plus 1. And we get that 2zb plus b on the left equals z minus 1. Let me get everything to do with z's on one side, since that's what we're solving for, and everything without z's on the other. So I'm going to subtract z from both sides, and I'm going to subtract b from both sides. That'll give me everything with z's on the left-hand side and everything without them on the right. So we have 2zb minus z, and then plus b minus b is 0, equals negative 1 minus b. Now to solve for z here, we'll just factor it out, and then divide by whatever's left. So let's factor out this z. We get z times 2b minus 1 equals negative 1 minus b. And let's divide by 2b minus 1 on both sides. And we get that z equals negative 1 minus b over 2b minus 1. So that's the z that works. So that tells me that f is onto, almost, I'll put a little star here, and the answer is because, well, in this step here we divided by 2b minus 1, so it's except when 2b minus 1 equals 0, which means that b equals a half. So what we're going to do is we're just going to say that our implied codomain, if we want this to indeed be a bijection, is we want to not have a half in our codomain, and in our domain, we don't want the element down here where we get 0. In fact, maybe I'll go up and show this in the original thing. We can't plug in something that makes the denominator 0. Then it's related to nothing. So we want to exclude where 2z minus plus 1 equals 0, which is when z equals negative a half, just solving for z. Okay, so we're almost done here. Let's just write down what we found. So our function f really goes from the real numbers, but minus the set negative a half, since we're not allowed to input that. So it goes from this set, that's our input set, to the output set of the real numbers minus positive a half. Because that's the only element that we can't get via the argument we just did. So here's what f looks like. Here's our implied domain. Here's our implied codomain. And f inverse of z, say, well, that's going to be, well, we're just going to replace the b's by z, so it's going to be negative 1 minus b, or sorry, not minus b, we're replacing that, minus z over 2z minus 1. And you can see, let's make sure that this works. So what is f of 2? Well, f of 2 is 2 minus 1